Yeah, as Jacques said, I'm going to talk about mainly modeling, in contrast to most of the other speakers at this conference, and in particular modeling of atmospheres and winds of evolved stars, mainly AGB stars. I should also point out right here in the beginning that I will be showing some animations in the end based on material that is not really published yet, and which is done in collaboration with Bernd Freitag, who is also online, and other members of the X-Wings team. The X-Wings project is an ERC project here at Uppsala. Okay, so let's see. Where's the... That's interesting. Since this is a mixed audience in the sense of what objects you're working on, I thought I'd start with a quick "you are here" slide. So in terms of stellar evolution, we are mostly looking at the asymptotic giant branch phase for low and intermediate massive mass stars. We also look a bit at red supergiants, but on this side of the diagram, we have gotten further theoretically with the modeling and so on. So during this talk, I will focus on low and intermediate mass stars, so on AGB stars, basically. And as you know, they will later on develop into, find my mouse now, into white dwarfs, maybe surrounded by planetary nebula. And we are studying how the mass loss is happening, how the wind is being driven. But that means that we actually have to understand the stars themselves to understand these processes. So what this talk will be about, this is kind of an outline here. I will be going from the stellar interior, starting with discussing pulsations. As you probably know, Myra is one of the first variable stars ever discovered. So asymptotic giant branch stars typically show large amplitude light variability, which is attributed to pulsations. They also show large-scale convection. We'll get back to that in a moment. And all of these dynamical processes create strong shock waves in the atmosphere. And this is important for driving or initiating a dusty stellar wind, which then leads to heavy mass loss. So again, as I said, starting inside out, these processes begin with pulsation and convection inside the star. And so typical periods here are 100 to 1,000 days. These are large objects, large timescales, and they are notoriously difficult to model, the pulsations. And this is because they are large amplitude, non-linear, non-adiabatic. So the usual linear models don't work in this case. And the large convective motion, so you're really talking about convection on scales of the stellar radiance, basically, on giant convection cells. They are not just an energy transport mechanism, but it's really a mixture, the dynamics of large-scale pulsations and large-scale convective motions. So what you need to do basically is to take a full star in a box approach and do this in full 3D to model it. I give you here a very quick overview of what such a model can look like. We'll go more into detail later. But here you see the surface intensity, a time series of surface intensity of such models. And you see that there are huge structures here on the surface, which are a consequence of the convective motions. So this is not just theory, as people sometimes say, but this is actually something that since in recent years can be observed. So what you see here is one example. that I took from a paper by Claudia Palladini and company. I think this is a very nice example of a resolved stellar surface. And I think on Monday, the different image reconstruction algorithms were discussed. So these are two different versions here. And you see that you basically see the same features in both images. Further examples of this kind will be shown in later talks. So I'm not going into the observational side of this, but I would rather like to show you what we have learned in terms of models. So this is a longer time series now of surface intensity plots from a cobalt model, so a 3D radiation hydrodynamical model that contains, so to speak, the whole star. And you can see again the large convective structures on the surface, but when you concentrate a bit, you can also see that the overall intensity of the image varies, so to speak. So here's rather low, here's rather high. So we see basically light variations here. The question is, are these things connected to pulsations? And the way to analyze this is to look at the structure of the models, the interior structure of the models. What I show here is a sequence of density slices through the center of the computational box. So you see this is rather the stellar radius, and inside you see convective motions, and outside you see shock waves in the atmosphere. And the right-hand side shows the radial velocity. So, sorry, blue means outward going, radially outward going components, and red means infalling material. So you see inside the star, you have this thing that always reminds me of like a section through a brain or something like that. The huge upwellings and downflows in between. So really giant convection sets here. So how do you make sense of this mess? Well, if you're looking for pulsations, one thing you can do is you can make spherical averages. So you average the radial velocities over spheres, and then you plot this as a function of depth and time. Then you suddenly see quite nice patterns actually here. So, sorry, so the stellar radius would be roughly here, and on the inside you see this pattern of red, blue, red, blue, red, blue. So standing wave, basically fundamental mode radial pulsations, and then in the atmosphere you see the running shock waves going outwards here. So if you do this for a number of models with different parameters and so on, you can plot the resulting periods against luminosity, as is done for observations, for instance. So the line here would be an observed period luminosity relation for Mira stars, and the colored symbols here are models. I should also point out this is work from several years ago, and we have a much larger set of models right now, and there is a paper in preparation with analyzing a much larger set of models. But in a nutshell, also these new models fit very well on the observed relations. So we really see self-excited pulsations going on in these models. And the reason why I'm stressing this is that pulsations are an important part of the wind mechanism. So this is actually a very old simulation here. So here the star would be roughly this size, and what you see as color here is the dust density. What you see in the upper right-hand quadrant here is shock wave running out. And this has reached a distance where temperatures are low enough for dust to form. And in this dense wake of the shock, conditions are right for dust grains to grow, and then radiation pressure on dust pushes the material outwards. What kind of dust do we expect? Well, if you look at mid-infrared spectra of AGB stars, you typically see features at 10 and 18 microns. And that would suggest olivine and pyroxene type silicates, so magnesium iron silicates. And from a theoretical point of view, that makes good sense because the silicates consist of abundant elements. They can form at relatively high temperatures, so relatively close to the star. But one of the questions that has been keeping us busy over the last few years is what is actually a typical iron to magnesium ratio? Because these features basically come from bending and stretching modes of the basic SiO tetraeder here, so it's hard to determine the magnesium to iron ratio. So in a nutshell, if you are on the magnesium rich end, material is very transparent in visual and infrared wavelengths. If you're on the iron rich side or even include a little bit of iron, then you get very high absorption in the near infrared and visual, where you have a lot of stellar light. So these grains are relatively cool compared to those who absorb a lot of light. So these can form a lot closer to the star than anything that contains even a little bit of iron. I should also say to drive a wind with basically transparent grains means that you have to do it by scattering instead of absorption. And that means you have to have the right particle sizes. For an AGB star with the stellar flux peaking somewhere around 1-2 micron, that means the grains should be somewhere in the range between 0.1 and 1 micron in radius. So what we have done recently, or what we did earlier, is we assumed basically that that the grains were made of iron-free silicates, but recently we have implemented that both types of materials. So the grains themselves decide based on radiative heating how much iron can be contained in the grains at what distance from the star. So you start out with something like this, get a wind going, and then in the wind you get an enrichment with iron. To show you one of the new models, so this is what it looks like roughly, the radial structure. And what you see here is the velocity, for instance. So I should also say the different colors here are different pulsation phases. So what you see here is shock waves. For instance, if you take the blue one here, you see shock waves, and then the whole thing develops into wind out here, so above zero. So sorry, this is a theoretical scale. So plus means outward directed motions, minus means inward directed. And you see how the shocks propagate through the atmosphere until they reach a point where the temperature is low enough for dust formation. The shock waves are also visible here in the density profile, and you see how it goes from a steep atmospheric decline, this is a log scale here, into a flat 1/r² profile for wind. For the grains, you see here how they start growing. This is the grain radius, and they grow very fast to the magical grain size where they can drive a wind. But what you can see here, if you look at the Fe/mg plot, is that the enrichment with iron sets in later. So they start growing, the wind starts going, and then when you go away from the star and radiative heating becomes less, the iron gets, sorry, I'm losing my mouse here. The iron gets incorporated. And what you see here, sorry, here is the dust temperature, the grain temperature. So you see this kind of plateau, which is a sign of self-regulation. So the amount of iron included is just such that you stay under the sublimation temperature of the grains. And this plot shows you the difference of the temperature when you have the iron included or compared to an iron-free grain. So you get substantial heating, even if you just include a few percent of iron in the grain relative to magnesium. You can get several hundred degrees of heating here. Like I said, the enrichment of the silicate dust is a secondary process in the wind, and the self-regulation leads to low values of iron to magnesium. Okay, we can get back to that later. Nevertheless, you get distinct mid-infrared dust features here. And this is something you don't get if you do not include the iron enrichment, because then the grains are too cool and they will not produce this characteristic emission here in the mid-infrared region. This is just to show that the combination of mass loss rates and wind velocities of the models here, the colorful stars fit well with observations, which are the black dots here. So we have learned from our models that we need relatively large grains. They will have very low iron to magnesium ratio. But what we also have learned is that the growth rates are very dependent on densities. So what you should expect is that the density distribution in the atmosphere is kind of reflected in the dust distribution. And but both of these things are basically things that are seen in observations. So I give you one example here, and I know that Keiji Onake is talking later today, so he will probably show more of this stuff. Here you have scattered light observations of W Hydra. The star would be roughly this size. And you see the light scattered by the dust around the star. And you see that it's not one spherical ring, so to speak, but you see that it is clumpy. And the grain sizes fit quite well, actually, with models. So what I have shown you so far in terms of models is 1D wind models and 3D models of the stellar interior and the inner atmosphere. What we have been doing recently is make a transition from these two types of, so to speak, classical models nowadays to global modeling of the star and the wind. So really from the stellar interior in full 3D out into the wind acceleration zone. And we can study the interplay of pulsation, convection, wind acceleration that way, and the emergence of structures in the atmosphere and wind. So without much further ado, I know that you're interested in structures and patterns and observable stuff. So here I will show you some very first results of these models. So again, this is a real global 3D radiation hydro model, including the star and its wind. Here on the left side, you can see a slice through the all of them are slices through the center of the star, through the center of the box. What you see here is the density, and the star would be roughly this size. So high values mean high densities, and then you get the low densities out here in the atmosphere and wind. What you see in the second panel here is grain radius. Black means no dust and bright means large grains. So of course, in the middle where temperatures are hot, you get no dust, but you also see that this is not like a round contour or anything like that. This is where this phenomenon that density is important comes in. So what you see is that the dust forms primarily where you have the shock waves in the triggered by convection and pulsation. And then where you have the dust grains, you see in the radial velocity plot, you see the blue velocities. So here material is getting accelerated outwards. And here you have basically a wind. So you see how these density enhancements translate into efficient grain growth and into acceleration. So you really get a feeling how the structures emerge in the wind. So
5 minutes.
So, yeah, perfect timing. So this is where we get to the animations, or rather the movies of these models. So this is now the first movie showing the density cuts through the center of the star. So again, the star is roughly this size. So you see the box is now huge compared to maybe what you have seen before in terms of 3D convection calculations. You see how shock waves form and move outwards. Here's another one. I think there's a nice one coming here now, and so on. So you see how the pulsation and convection in the star triggers these shock waves in the atmosphere. And these are the locations where you get efficient dust formation, and this is where the material then gets pushed out by radiation pressure. Let's look at the corresponding movie for the dust grains, grain radii. So here you see a new one emerging. I think there will be another one soon. Here, and then this material gets driven out. But sometimes you also see that you have short flashes, so to speak, of dust formation here now, or here. So not all dust that forms makes it actually into the wind. So since the star is pulsating and the luminosity is changing, radiative heating is changing, and dust that has formed during a relatively cool phase can be evaporated again before it manages to accelerate the gas outwards. But you see how, in principle, this structure of the shock wave translates into dust clouds, and how these dust clouds lead to outward motion. So here we have the third movie showing the radial velocity. What is nice here is now you don't just have a black hole in the middle, but you really see the convective patterns inside the star. So these are these upflows and downdrafts that I mentioned earlier. Star is roughly this size. Then you see how the shock waves form here. Dust gets formed in the shock waves and the material moves outwards. Here's another one. So you see how this is happening again and again. And in the end, you basically get a nice outflow here already at a few stellar radii distance. So as I said, this is material that we are writing up for a paper right now. And if you can't wait for the paper, you can find some preliminary results in the proceedings of the IU Symposium 366, which was held, well, actually online, but basically in Leuven in November. This is actually available on the archive now since a few days ago. There's also a poster out there by Joachim Wiegert, who is actually in the conference room, or should be in the conference room. And it tells about our plans to produce observables from these models. So this brings me to my conclusions. So the high angular resolution imaging has really shown that the circumstellar medium in the closed circumstellar environment is clumpy, both the gas and the dust, and these kind of structures can be very naturally explained. They emerge directly from 3D star and wind box simulations. What you probably need is relatively large, large for stars, I should say, not for people who are used to circumstellar disks. Large grains to drive these winds. There are indications that you can find these kinds of grains at the distances where the wind starts. They will have low iron to magnesium ratio, but they will be gradually enhanced, and this should be something that is observable with mid-infrared spectrophotometry. We did some test calculations a few years back. I can tell you more if you want to know. Yeah. Finally, I also mentioned that for supergiants, it's still unclear how the wind mechanism works, but there are indications that there might be some similarities with HEB stars. We are just not yet there with the models, so we cannot draw any firm conclusions. Thank you.
Thank you, Susanne, for this wonderful talk and these wonderful simulations. Are there any questions in the audience? If yes, please give your name and affiliation before asking the question. And in the Zoom, you can ask questions in the chat or just raising your hands. Okay. There is a question from Jinhua He. Please go ahead.
Okay, thank you. It's very, very beautiful. But I have the impression that most of the models show that the AGB stars or the supergiants, they are very irregular. So, but in observation, we usually see the circumstellar envelope of the star is nearly spherical. So I want to know whether you can reproduce such kind of nearly spherical envelope of AGB stars from your model.
Yeah, I think it's a matter of scales. So these movies, they show you the close environment of the star and the short sequence. So what you get in the end is that, you know, you get clumps going out in random directions over time. So when you look at the larger scale, you get a very spherical picture, basically. So we're not expecting sort of big deviations from overall spherical symmetry, but what we are expecting is a certain clumpiness of the material.
Okay, thank you.
Okay, there's a question from Marcus Witkowski.
Yeah, hi Susanne, can you hear me?
Hi Marcus.
Yeah, so I've been thinking about chromospheres recently. We see chromospheric lines in the UV and in the optical, for sure for red supergiant, but I think also for AGB stars. And we see these temperature inversion in ALMA radio continuum data. So I wonder if you can relate any zone in your models to such chromospheric lines.
I think here again the clumpiness comes in. I don't think that there will be like a spherical zone, so to speak, where you get high temperatures, but there are. I would guess you get small zones with relatively high temperature related to shock waves. So we have been discussing stuff like that. For instance, when shock waves collide, for instance, if shock waves collide sideways and so on in the inner atmosphere and so on. At the moment, the spatial resolution in the models is not high enough to get. Probably these zones are very small and very thin, so you need don't need a lot of coverage in terms of volume, I think, or surface fraction or whatever to produce these things. I think that's gut feeling at the moment. So if you can, I think what you would need is better resolution and study these things in detail. But I would guess it's something that is happening locally, and you don't get like a, well, you don't get chromosphere, not a sphere in that sense. That's what, but that's my best guess because the models are not there.
Okay, thanks.
All right, there's a few questions from the audience.
Hi, it's Chris Haniff here. Susanne, can I ask what the challenge is for doing the modeling of the red supergiants? Is it just the larger scale of convection, or there are other physical issues that are difficult to manage?
Well, actually, relatively speaking, the convective cells are smaller. So one of the issues is resolution, but that's not a serious issue. The question is if there are other processes that come in. So as you probably know, the current supergiant models with cobalt coat, they don't have enough atmospheric extension so the convective pattern looks good, if you compare to observation. I'm sure Andrea will be talking about stuff like that, so I don't want to go too deeply into this. But in the radial direction, so to speak, you don't have the extension that you need. And we have a few ideas about that, and we are looking into various processes that might be missing in the current models, which since the stars are more luminous and a bit warmer, it's a slightly different physical regime than in the AGB stars. So things that might not matter in AGB stars and that are not in the models at the moment might matter in supergiants. So sorry for being a bit vague, but since it's not done, I cannot really give a conclusive answer on that.
Okay, thank you. Sorry, unfortunately, we don't have time for more questions. I see that few of them still, but please use the Slack channel for asking the questions there. I'm sure Susanne will be happy to answer. So great, thank you, Susanne, again.